Okay, so let's do the Hadamard test. Okay, so what is the nature of the Hadamard test? Let's talk about that. Remember, it's sort of just trying to solve this problem. Okay, so Hadamard test. Here's how it goes. The inputs, I'm going to say R, and n qubit, an n qubit, I should say m qubit unitary. And actually, I'm going to say for some reason the code for R. Okay, we're also going to assume that the input is some qubits, A1 through AM, in a state start. Promised to be in some plane of rotation P that R rotates by theta. So as I said, actually, for just a generic, unitary, it has all these different planes of 2D planes that it rotates in. And like most vectors are not in any of them. They're in like some linear combination of them. But we're going to assume, like as a promise, that the starting state is actually in one, it's like lying entirely inside one of them. And what are the outputs? So one output is going to be a random bit, a classical bit, D, which is either 0 or 1, D, which is 1 with probability sine theta over 2 squared. Okay, and that's pretty good because that's sort of what we were looking for here. We were looking for some signal that occurred with sine of the angle we're interested in squared. Here it's like sine of half the angle we're interested in squared. But that's fine, whatever. I mean, estimating theta over 2, it's the same problem, just multiply your estimate by 2. But moreover, besides spitting out this random bit, which solves, is towards solving this problem, the qubits A1 through AM are not deleted. They remain. And there are in a new state. So their state will change. I'll call this new state ket new. But the key point is that ket new is in P. Okay, so this leaves the qubits A1 through AM alive. And it does change their state. But their new state is some other vector, which is also still in P. And I'll go over this later, but you can see, well, maybe I'll go over this now. Let me remind myself. You can see maybe why this is helpful. Not only do these qubits not get deleted, but we can reuse this for like our next measurement. So indeed, I guess I'll say that now. So we'll eventually, give the Hadamard test and prove that it has these properties. But now let's understand why, given that it has these properties, we can still do rotation estimation in this hardest setting. Okay, so assuming, take my word for it, the Hadamard test has this property. Let's see why we're now kind of like here. We can still do rotation estimation in the hardest setting. So I'll just recall things about the algorithm. Recall it relied, each of these stages kind of used this interval estimation, which again was just like making a starting state, rotating, measuring. It just needs to be able to repeatedly and this repeatedly is important, get random bits d which are 1 with probability sine theta squared. Okay, but as I said, here we pretty much get this. We get like, random bits d, which are 1 with probability sine theta over 2 squared. So, okay, our interval estimator will estimate theta over 2 rather than theta, but then we can just multiply the estimate by 2, so that's fine. And moreover, as for the repeatedly business, like after the first Hadamard test on ket start, we can do another one, and then another one, and another one, and another one. We can do another, and another, and another. Because this new state, ket new, is still in P. So it can serve as like the new start for the second Hadamard test. Okay, so with this new state of A1 through AM, we can do another Hadamard test, get another random bit d, which is 1 with probability this thing related to theta. And then the qubits will get into some third state, but this third state will also be in P. So we can call that the new start and just do the Hadamard test over and over again. Okay, so this bullet point is like fixing the difficulty we faced of like, oh, we can't recreate ket start. Well, we can't, but we like get a state back that's still in the same plane, P, so that's good. Okay, so yeah, by virtue of this, it means we can do like the whole rotation estimation algorithm, even in this like most challenging setting, except for the glitch. But I'm going to say something about the glitch once again at the end. There's some like stupid annoyance about that. Because you remember the glitch, like in the middle of rotation estimation, you had to be able to do some like offset fixing rotation yourself by hand that was like a multiple of 45 degrees. But now you're like, oh, but now we don't know anything about P. How are we going to do that? In the Grover setting where we were able to fix that, because we did the is medium thing, we found something that was near 45 degrees, but like here it looks like a real problem. At the end I'll say like a couple sentences of fine print about why it's not a problem, but never mind about it for now. Okay, so remainder of this lecture, how to do the Hadamard test. What is a Hadamard test? Why does it have these properties? Then, assuming there's time, I'll write like a gigantic board where like I just draw a gigantic box and I'll be like, this is the rotation estimation algorithm's behavior. You can now completely forget about how it worked and like only remember like the interface to it. And then maybe I'll say some words about the dumb glitch, or I'll say you can read the fine print, which are in the notes. Okay, so great, the Hadamard test. I'm going to write the code for it here. It's actually not very hard, or at least the code is short. Okay, Hadamard test. Okay, and again, you should imagine that like the Hadamard test like has the code for R, so it's going to do some like R in here, and moreover, kind of like the input are some qubits, like A1 through AM. It's going to assume A1 through AM already exist and are in this starting state, ket start. Right, it's got to like make one output bit and also leave the qubits A1 through AM alive. So okay, line 1, it's going to make one new qubit called capital D. And you can think of D as standing for data because it's going to like produce our data bit, but like maybe you can also think of it as meaning, do I rotate? Because what we're going to do now is we'll do good old add and diff on D. Or if we were doing the normalized version, this would be Hadamard, and apparently this is the reason it's called the Hadamard test. But anyway, this puts D into like sort of an equal superposition of 0 or 1. It's kind of like we're going to use that to like go into equal superposition of do I rotate start or don't I rotate start? So in particular, in line 3, we're going to do this. If D, then do R on the qubits. Now, I'm going to come back to this soon, because this is actually not doing R. This is doing what's called controlled R, or like if qubit, then R. And if somebody just gives you a box that does R, it's not actually clear how to do like a controlled version, like if D, then R. But we have the code for R. So as I'll say in a second, it's fine. By virtue of the fact that we know how to execute R, we can also execute this controlled version of R, where we do R if and only if this one qubit is set to 1. And interestingly, here we set it to like an equal superposition of 0 or 1. So it's kind of like in one piece of the state we're doing R, and the rotation, and the other piece we're not doing it. Then we kind of interfere those two branches back together by doing average and div on D. And this is kind of going to be like, at a high level, like comparing or combining what you get when you do the rotation to start and what you when you don't do it. They kind of get combined in this line, as we'll see. And then the last step is just to extract D. Okay, that's the whole algorithm. Okay, we're going to analyze this, and it won't be too hard. But let's just first pattern match it against the specification. It does indeed output a random bit D at the end here, so we have to check. We have to like calculate what is the probability that this will be 1. And it does still leave the qubits, A1 through AM. They're not deleted or anything. Also, no other qubits are created, because D comes into existence, but then it goes away. And so they're going to be in some new state. And so we do have to sort of check that this new state is also in this two-dimensional plane of rotation P. Okay. Now, before we have the pleasure of analyzing this, which is pretty fun, actually, let me just say a few words more about how we do step 3, the controlled version of R. And it's not that complicated or anything, but I just want to like also partially remind you, like in the end, we got into this like very abstract setting where we have like rotations and space and so forth. But in the end, this R is like some giant block of code with like toggles and Hadamards and if A then toggle B and so forth. And it's like, let me just do like a little example to illustrate the point. Like, maybe, for example, say the input code for R is like this, like R, maybe M is 3, R is some routine that takes in 3 qubits, and maybe it's like, oh, toggle A1, and then like, if A2, then toggle A3. And then, I don't know, Hadamard A2. And then, I don't know, maybe the last line is if A1 and A2, then toggle A3. I have no idea what the specific code is. I just made up like 4 random instructions. But like, just to remind you, like, okay, this like lecture 3, lecture 1, lecture 2 stuff, R might be this code. And what I want to say is like, it's almost like you copy paste these 4 lines into here. That's almost what you do. If this just said like, do R on them, then you would literally copy paste like all the lines of R like into here. But that's not quite right. You need to like accomplish if D, then do all these instructions. But that's fine. That's easy. You basically just prepend if D then to all these lines. Now, you have to think about it a little bit how to do that, but it's fine. So we're going to make like this new block of code that's like if D, then R on A1, A2, A3. Okay. And this is like, the algorithm just does like some like text edit on this. Like it'll be like, all right, so this will become if D, then toggle A1. That's fine. This is a normal 2-qubit instruction. Okay, now it's like, all right, I want to like do this condition on D. So if you think about it for 2 seconds, that means you want to do if D and A2, then toggle A3. And that's fine because you're like, oh yeah, this is like a basic instruction that we were allowed back in lecture 3. It's like a 3-qubit instruction. Okay, and then this one, you'd be like, okay, we kind of want to do like if D, then Hadamard A2. Now this is a 2-qubit instruction, and like with tremendous foresight in like lecture 3, I told you, like I gave this as an example instruction. I was like, you can do this one. So great, like this is also an allowed instruction. And now this one is like a bit of a pickle because, not really, but like you kind of want to do like if D and A1 and A2, then toggle A3. But this was not like one of our allowed instructions like back in the olden days. We allowed this kind of thing, but not this one. But it's not a problem, right? Like maybe I made you program this on like homework 1 or something. I can't remember. But like, this is not a basic instruction. But you can program this easily. It's like a little exercise in, I don't know, 2 or 3 lines. I didn't bother to check, but like, yeah, you'll need to like new 1 more qubit and like, I don't know, and then delete it again. But you did this kind of thing back in the early part of the course. Yeah, and of course, you can't really solve this. You could say like, oh, I'm going to allow this as a basic instruction, but then you'd get into like a catch-22 because then like that instruction might have appeared here, so then you'd need to like allow the controlled version of it as well as a basic instruction, and you get into an infinite regress. So we'll just like stop and say like, okay, this one you have to program yourself in like 5 lines. It's probably more like 5, or 6, I don't know. Okay, so this is all just to say, this is like a little aside to say that like we can do this. But you kind of need the code for R in order to do this. But that's okay because like we're going to have the code for R because R will be something we ourselves made based on the number we're trying to factor.